Welcome to Beyond Where, modeling spatial relationships and making predictions. My name is Flora. I am a product engineer on the analysis and geoprocessing team. I work primarily on data visualization tools like charting and Pro. I am also a product engineer on the online analysis team, and I help design and build the analytical tools that we provide in ArcGIS Online. And these are my colleagues, Alberto and Janora. Alberto is a solution engineer out of our DC office, and he works with our federal customers, helping them solve problems with these analytical methods. And Janora is actually a member of the spatial stats team, unlike Alberto and I, who are kind of like honorary members of the spatial stats team. Janora is on the spatial stats team, and she's responsible for the documentation of all of the tools that we're going to be looking at in this session, and then also in the other workshops that belong to the spatial stats series. So this workshop is all about modeling relationships. So what does it mean for variables to be related? Well, when variables are related, you can learn information about one variable by observing the values of other variables. So it's helpful for me to to visualize it like this, to see these shapes, right? If the relationship forms some sort of pattern, some sort of shape, then we can predict. If we see that linear relationship and we know the value for X, we can take a good guess at what the value for Y would be because of that line that we have. If we have a more complex kind of relationship, like a convex shape or even kind of like a sine wave, all of these relationships help us learn about one variable by predicting where it would fall along the line based on the values that we have for other variables. And why is it useful to model relationships? Well, we can explore correlations, so see how things are related in a linear way. What we really are after in a lot of these cases is predicting unknown values, right? So we know the relationship, we see that there's some sort of pattern. As one variable changes this many units, the other variable is going to change that many units, and that helps us predict unknown values. Even when we can't say that one variable changing causes the other variable to change, if we know that they change together and we need to make a prediction, we might be able to use one variable's values to predict the other. And then we can understand key factors. So we can understand things that may or may not cause a unit of change in one variable. But we have to be careful, right, with correlations. Because oftentimes, things that are not actually related to each other can have very strong correlations. For example, the divorce rate in Maine is very strongly correlated to the per capita consumption of margarine. Now, I've never been married, but I have a feeling that margarine is not causing divorce. I mean, butter is obviously better, but I don't think that in order to decrease divorce rates, we need to get rid of margarine. Similarly, the number of people who drowned by falling into a swimming pool is very correlated to the number of Nicolas Cage films. Again, not a huge Nicolas Cage fan myself, but it is not causing me to run out and jump into a pool to my death. So, are any of you familiar with Xkcd, this webcomic? It's one of my favorites. It's lots of really nerdy jokes, and this one is very appropriate for this workshop, I think. I used to think correlation implied causation. Then I took a stats class, now I don't. Sounds like the class helped. Well, maybe. So we do have to be careful. But when things are correlated, even though we can't say that one causes the other, we still might be able to use that for prediction. So we could say that ice cream sales, when ice cream sales go up, crime rates go up, because those things typically go up in the summer, right? So I can't say that ice cream sales cause crime. I'm not gonna be able to fight crime by reducing ice cream sales, but if all I had were ice cream sales and I had to do my best guess at guessing crime, I might be able to use that number to make a slightly more educated prediction. But I could definitely not say that one causes the other. So we're going to be looking at some linear methods in this workshop. We do have another workshop that we're teaching at 4 p.m. today about a different method, a machine learning method called random forest. And that talks about a different way of modeling. But in this session, we're going to be talking about linear regression. And this is more of a statistical method, whereas the random forest is more of a machine learning method. And we're going to be talking about generalized linear regression and how we can use this method to predict unknown values and model spatial relationships. So I'm going to hand it over to Janora, and she's going to walk us through how this works.
All right, so generalized linear regression is a regression method for estimating and modeling linear relationships between variables, and then using that model to generate predictions. So we're going to start by going over the math, but I promise this will be painless. It's only going to take a minute, so don't leave. We're really just going to use this math equation as kind of an illustration or a map to go over the vocabulary. It can be really helpful to map back to. So the y is the dependent variable. So this is the phenomena that we're interested in, what we're trying to predict, understand, and model. So y equals something based on everything on the other side of that equation. The x's are the explanatory variables. So these are the variables that you believe cause or explain or are related to that dependent variable that you're trying to model. They're also called independent variables. And then we have the coefficients, which are these funny looking b's, and they all come before the x's. And these coefficients represent the strength and the type of relationship that the explanatory variable has to the dependent variable. So for instance, you could have a positive relationship. So as obesity rates rise, so do diabetes rates. You can also have a negative relationship. So as foreclosure rates rise, home values drop. Or there could be no relationship at all, in which case you might want to consider dropping this particular explanatory variable because it's really doesn't need to be included in the model. It's not influencing the prediction itself. And finally, at the end of the equation, we have the residuals. So these are the model over and under predictions. So when we're creating this model, we're basically creating a prediction line. And it's based on all of the values that we know. And we can compare the predicted value to the observed value. But because no model is ever perfect, those values, the observed values, probably fall either slightly above or below that prediction line. So when the true value is less than the predicted value, we have an over-prediction. So our model predicted higher than our known value. And when the true value is more than what we've predicted on that line, we have an under-prediction. And these over and under predictions are really important because they represent what is not being explained in our model. So Alberto is going to show us how GLR works in action.
Okay. Hello, can you guys hear me? Great. Okay, so we have data for Medicare spending per capita across the country, and we've run hotspot analysis to try to determine statistically significant clustering of high Medicare spending. If you think about it, it should be pretty even throughout the country, maybe a few higher values here and there, but it really shouldn't be quite like this. So perhaps in the Southeast, maybe they're spending more because they're taking such great care of all the patients there, right? Perhaps. So there's a hospital readmission rate data set here that we can take a look at as well and just visually compare. If you think about hospital readmission rates, these are people that were readmitted within 30 days, and you can make a case that perhaps they weren't well taken care of if that's the case. So areas with high hospital readmission rates may be indicative of low healthcare conditions there. And they actually just visually comparing this layer, this output of hotspots analysis to this layer of hospital readmission rates, you actually see that in the Southeast, that's not the case. You have high hospital readmission rates. So we need to explore a little bit more. So we're gonna make that a study area. And we have, here we have a choropleth map of total costs in 2010. So we can take a look at a chart of the relationship between total costs and average HCC score, which is an index that measures health based on the prevalence of chronic conditions. This R-squared gives us a small sense of that relationship, so we can actually test that very briefly using generalized linear regression. I'm going to go ahead and pass our input hotspot study area. Select total cost as our dependent variable. And we're going to keep the model type as continuous, but we're going to go ahead and select average HCC score, that index, as our explanatory variable. And we'll run the tool. A quick note, how many people have clicked this little icon at the top right of the tool before? Yes, okay, so click it every time you're starting to learn a tool because it takes you to the documentation, and the spatial stats team does a really good job documenting everything about the tools and how they work. So everything that I'm talking about and everything that we'll be talking about, it's actually really well documented here, and it takes you through how to run the tools. So here's the output, and let's take a look at the messages first. So the messages are just as important as the layers that the tools produce in many cases. One of the primary factors that we'll take a look at, or one of the main diagnostics that we'll look at, is adjusted R-squared. Let me make that a little bit bigger for everyone. It's about 0.65, just like we saw in the chart. But also, another factor that we're looking at to evaluate the accuracy of a model is the clustering of the standardized residuals. And here you don't really have to run much more analysis to see visually that the residuals are clustered. There's an east-west divide that we can perceive. So we're missing some information that can help explain total costs here, right? So perhaps we can add additional variables. So let's go ahead and remove HCC score. We're going to add the amount of hospital beds, evaluation and management costs, imaging, so like CAT scans, MRIs, that sort of thing. We also have the distance to Houston. So I actually have a feature here that is just a point right over Houston. So that seems to be an explanatory factor. Houston actually has one of the largest Medicare facilities in the whole world. In order to calculate the distances for every feature to Houston, you could do that separately, or you can simply drag and drop the Houston feature class to your explanatory distance features parameter, and it'll calculate those distances, which is really great. And then from there, we can also add PQI-10D, which is actually a measure of dehydration rates. So let's go ahead and run that. And we'll take a look at the results. So our adjusted R-squared has improved quite a bit. It's 0.86. We're now explaining 86% of the variability there. And with respect to the standardized residuals and how clustered they are, this is a little bit tougher to make a judgment call on, right? So let's actually run a tool called Spatial autocorrelation to try to figure out if these standardized residuals are actually clustered or not. So let's pass our output of GLR, pass our standard residuals as the input field, and let's select to generate a report so that you can get a sense of that. And once again, click your output results. You get a report file here. You can just click that link. And we can see in this case that there is no clustering or dispersion. It's random, which is what we desire for an output of a model of this type. And now we're going to pass it back to Janora.
Okay, so Alberto made that seem very easy, right? But anybody who has anybody used OLS or GLR before? It's not always that easy. It can be frustrating and tiring, and you really need to have patience and a lot of research and maybe some magical fairy dust and a bit of good luck in order to find a good model. And again, as Alberto kind of mentioned, there's some other checks that we need to make sure, and other assumptions that we need to make sure are checked off in order to be able to trust our model, in order to be able to use it for prediction and things like that. So in order to help you find a model that you can trust, we have a bunch of different diagnostics to help you make sure that it's properly specified and that you can trust it. So we're going to run through a couple of diagnostics really quickly, but one more plug for the documentation. It actually is helpful, or at least I hope it's helpful. So we're going to run through these really quickly, but the documentation deep dives into all of these diagnostics and a couple more. So one more plug for the documentation. So the first thing that we want to check, we want to make sure that every variable in our model is statistically significant. We want to make sure that all the variables included are telling an important part of the story. So when you look at the messages window, you're going to want to make sure that there's an asterisk besides the probability for each of the variables that you're including in your model. So we want the variables to be telling an important part of the story. We also want the variables included to be telling a different part of the story. So let's say we're modeling housing prices, and you have one variable that is square footage and one variable that is number of bedrooms. Those variables are kind of getting at the same thing, right? They're describing how big is the house. So including redundant variables like that can cause model instability issues. So you really want to make sure that the variables that you're including are just describing different parts of the model, the things that you're trying to model. So we can measure this using a variance inflation factor, the VIF, and we really want these numbers to be below 7.5, but the lower the better. So if you do, if you're trying to create a model, you're never going to have one redundant variable, right? You're going to always have two. So we suggest taking one of the redundant variables out, running the model, then switching them out, and you would keep whichever one performs better in your model. As Alberto mentioned, the residuals should not be clustered in location or in value. So we can run the spatial autocorrelation tool to make sure that there's no spatial autocorrelation in our residuals. And then as far as value, we want to make sure that the residuals are normally distributed. So we want most of our over and under predictions to be close to 0, and then you might have fewer and fewer that are larger than that. And we can test for this using the Hark-Barra statistic. And in this case, we want the Hark-Barra statistic to not be significantly significant, so no asterisk. And then also our model should have a strong R-squared. And honestly, this is probably the diagnostic that we all check first. It's probably the most exciting one. But the truth is, if you haven't checked all of the other diagnostics and checked all of those other assumptions, we can't really trust a model, right? We're going to end up with a model that is the 0.99 for divorce rate and margarine. The last one I just want to mention is when you're comparing different models with different variables, when you're switching out the variables or using different settings, different neighborhood settings, you can compare the AIC score, and the lower the AIC, the better. Did you want to talk about exploratory regression, or do you want me to really quickly? Yeah. So
yes, it probably looked a little bit too easy in the previous demo, so we have some confessions. This model that we created with those 5 explanatory variables, it came after a lot of trial and error by Flora, and their help actually helped me present this. But actually, another tool really helps you get to that point, or at least help you make progress to finding a well-performing model. It's called exploratory regression. And exploratory regression is really useful if you're trying to just make some headway into getting to that model that you can trust. In this case, we've passed the input features for our hotspot study area. Once again, the dependent variable is your total costs. And you can pass it a series of potential or candidate explanatory variables that could be evaluated as a model. Once you run this tool, it's going to iterate. So it's going to test one variable at a time first, try to see how good of a model you may receive out of that. Then it's going to try 2 at a time, then 3 at a time, then 4 at a time, until you have, and that's actually a parameter that you can establish in the tool, how many to try. So here's the main output of the tool is actually the messages window. So take a look at that. Let's go ahead and expand that a little bit. And choose one of 11 summary. Essentially found that one of the variables performed better than the rest, the one I already took a look at earlier. Now we're going to try 2 at a time. Then we find a model that has the distance to Houston, the average AIC score, and so on. but no passing models yet. So there's actually just a summary of R-squared results, and then there's a passing model section. You'll notice that just by choosing 1 at a time, 2 at a time, 3 at a time even, we haven't found passing models, even though the R-squares are getting a bit higher. So it's doing all of those checks for you. It's really, really helpful if you're starting to learn how to make progress towards a good model. It's not until we get to choose 4 of 11 summary that we find some passing models. And the one that we're going to actually focus on is choose 5 of 11 summary. That's how we landed at something that actually performed quite well. The model that included, this one right here. The model that included hospital beds, evaluation and management costs, et cetera. So that could be a very useful tool as you're getting started. We're going to hand it back to Janora.
I do want to note that we don't necessarily encourage people to just like throw everything and the kitchen sink in the exploratory regression tool. The variables should kind of make sense already, but it is useful. And it's not a magic tool. Like sometimes you also have to run exploratory regression a couple of times, but it does have, at the bottom of the messages, it tells you a lot of information about the different relationships between variables and and that can also be helpful when you're starting out and exploring your data. So. The next tool that we're going to talk about is geographically weighted regression. And just another note, so you might have noticed that we're talking about GLR and not OLS this year. And about a year ago, we went through and renovated, added a couple different model types that Flora is going to cover in a little bit. But OLS is still in the software. You can still use it, but we have, like I said, renovated these 2 tools. Hopefully they're a little bit friendlier user experience and things like that. So the next tool we're talking about is geographically weighted regression. So GLR and GWR are both linear models. The difference is that GLR is a global model. So you're creating one equation for your entire study area, and you're using all of the features in that study area to calibrate the model. With GWR, each feature gets its own separate equation, and that equation is calibrated using only the data from your neighboring features. So the coefficients in one part of your study area are going to vary from the coefficients in another part of your study area. So each feature in your study area is going to get its own equation. And I think this is really cool. It kind of reflects Tobler's law, the first law of geography, that things that are closer together are more related than things that are further apart. So what it's saying is my neighbor is going to be better probably at predicting my value than somebody across the country or somebody in the 3D demo across the hall, which makes sense. Like I said, we kind of renovated GWR and included a couple different options for how you define local neighborhoods in your model. So you can choose a neighborhood type of number of neighbors. So it doesn't matter how big or small your polygons are in your study area. If you set it to 20 neighbors, each feature's equation is going to be calibrated using 20 neighbors. You can also use distance band. So for distance band, your larger polygon features are going to have fewer neighbors that fit in that distance band than areas where your polygons are smaller or denser. We've also revamped the neighborhood selection method. So basically the tool is going to increment out and find the best performing neighborhood for your model. We've implemented golden search. So this is going to smartly kind of increment by thirds, like increment those distances to find an optimal distance for you. You can also use manual intervals. So if you know you want to search from like 10 meters to 100 meters and you want to increment in 10 meters, you can set it that way too. Golden search is looking for it's called the local minima. So it's trying to smartly, not guess, but like smartly calculate where that local minima is. Or user defined. So if you have one distance that maybe you've used golden search and you're rerunning the model, so you already have your optimal distance, you can just set a user-defined distance, or if you have a distance that makes sense for your analysis, you can go ahead and just input it that way as well.
All righty. So let's take a look at how geographically weighted regression works. The tool can also be found within modeling spatial relationships. Let's go ahead and select it. And for our input features, in this case, I'm actually going to use the output of GLR, Generalized Linear Regression, because we calculated those distances to Houston. They're actually part of the table now. And that's really useful. As Janora mentioned, it's not this simple case where you just pass everything to exploratory regression and you'll find your perfectly performing model, or you just run modeling once and you find your model. It's this iterative process. It's messy. It's not going to be quite as clean as you may want it to be, so you're going to have to iterate several times. So calculating these distances is actually very useful if you're using those variables. I'm going to select total cost once more and those 5 explanatory variables that were quite useful in our previous case. And then there's the distance to Houston that was calculated by the tool. We can go ahead and select that in this case. And now for the neighborhood type, as Janora mentioned, the geographically weighted regression process uses a neighborhood to create that equation. So we're going to select number of neighbors, and I'm not sure quite yet how many neighbors I need. And this is where you can select one of those methods to determine that. So we're going to select golden search. Each of these parameters also has a little bit of documentation within it. So I recommend, if you're not terribly familiar with them, just take your time and read each one of these and really think about it. And we're going to go ahead and run the tool. Excellent. So with generalized linear regression, by default, let's take a look at the results first, and then we'll take a look at some of the output layers. So that all important, well, actually, let's take a look first here at the golden search results. You can see the comparisons that it starts to make. It starts sort of ping-ponging back and forth between these different numbers of neighbors until you find a suitable AIC, a suitable measure of how different models may perform. So in this case, it shows the number of neighbors of 92. And then moving forward, we actually see an adjusted R-squared of 0.87. So it's getting better. The fact that we're integrating geography into how those equations are determined is really powerful. There's local relationships, right? And then also, when the tool is done running, it gives you the layer that visualizes standardized residuals. But you actually, because you have these local equations, you have a few other options to symbolize by. I'm going to select our coefficient, specifically the coefficient that is related to that dehydration rate. And let's go ahead and select a different color scheme, perhaps something like blue. And something that's really important about analysis, always when I run anything by Flora, she tends to ask me, what is the question you're asking again? And then what are you going to do with that answer? And very often I'm like, I had no idea. But it's very useful to think about what people are going to do with these analyses outputs, right? So something that could be useful is perhaps, in this case, the symbology that we're showing is how much dehydration rates helped explain total costs in our study area. And you're not going to have all the resources in the world to tackle dehydration rates across the United States or even the Southeast. But perhaps by looking at how dehydration rates help explain total costs in specific ways, maybe in more pronounced ways, you can target an effort just to a specific part of this region, right? And this type of view is quite useful for that. There's also a few other views that you can use. You get also attributes related to the local R-squared, the coefficients as we saw, the residuals, or the condition number, which is related to how hard the tool had to work to find a suitable equation there, and also your predictions themselves. So GWR is quite useful. Now we're going to hand it back to Flora.
Yeah, I mean, that point about what are you going to do with the answer, I mean, sometimes it's just useful to be able to find what's related so that you can predict. But if you're trying to do something about it, so let's say that we find that distance to Houston has a big impact on Medicare spending, we can't tell everyone to move closer to Houston. Like, that's not going to solve the Medicare spending problem, right? Like, we can't change how far people live from Houston. But with something like dehydration admissions, we might be able to implement some programs to educate our elderly on how to stay hydrated. So that's actually something that's actionable. You know, it doesn't mean that it's not useful to learn about things that are related that we can't really take action on, but in addition to that, we want to find things that we can actually do something about. And I did also want to mention, like Janora said, we're still running OLS under the hood in the new GLR tool, Generalized Linear Regression. And the reason that we're calling it GLR now is because we've included 3 different model types. Before, we just had continuous, the Gaussian model, which is ordinary least squares. But now we've included 2 other model types. And even when you're running OLS in ArcGIS, there's actually no difference between, it's ordinary least squares. It's a tried and true method. It's been around for a really long time. And when you run OLS in ArcGIS, it's the same as running OLS in R, or running OLS in SAS, or running OLS in Excel, or doing it by hand. It's the same method. One of the great benefits of doing it in GIS is that you can visualize the results spatially. So like that map of the residuals that Alberto looked at and to check if the residuals were spatially autocorrelated, that's really valuable. So especially when you're modeling spatial phenomena, it's really useful to do it with the map. So now that we've expanded the tool to include some other model types, it's really useful to talk about what kind of data is appropriate for each model type. So the one that we're most familiar with is this Gaussian model. It models a continuous variable. So that's the ordinary least squares method. That's the method that we just took a look at. And that's going to be for things like modeling healthcare spending, temperature as a continuous variable, sales profit, mortality rate, things that can fall anywhere along a number line. And when we're using a continuous model, we really kind of want our data to be normally distributed, to follow that nice bell curve shape. And if it doesn't fall along that bell curve shape, there are a couple different things we can do about it. One would be to maybe convert it to be a binary variable. So we could use logistic regression instead, which is modeling a binary variable. And we could say, okay, well, does it fall above or below the mean? And then we might convert that into zeros and ones and run our continuous variable as a binary variable falling above or below a certain threshold. Other types of logistic model examples would be the presence or absence or something. Do we expect that we will see the presence of a certain disease here or not? Will we see a certain species here or not? Will we see fire damage or not? Is this insurance fraud, yes or no? Are we going to pass or fail an inspection? Things like these yes or no questions, to be or not to be. And then we also have the Poisson model, and that's for modeling a count variable. So these have to be positive numbers, and they have to be integers. They can't have decimals, so it's like crime counts. Like we can't have half a crime, right? So number of traffic accidents, number of sales per month. And then it can also be used for these types of rates, like number of people with cancer per 10,000. So it's a kind of like a count per a certain amount, which is a rate, but it's still a count variable. So something to consider when running a Poisson model is that you might first run a logistic model to determine where it's possible for something to happen. So we might be counting, crimes, for example. And this might be a little bit of a silly example, but hopefully you get the point. There are some places where crime can happen and some places where crime can't happen, hypothetically. So you might first model, is it possible for crime to happen in these places and over this study area? And then we'll take out places like, the middle of a lake or something, because crime can't happen there. And then once we have the surface of where crime can happen, then maybe we'll take those features and run a Poisson model to do a count model and try to see how many might happen in those locations. And then logistic, of course, like as we mentioned, is those binary variables. So let's take a look at a quick demo of a logistic geographically weighted regression model.
Okay, thank you, Flora. So here we have a data set of inspections for locations in Chicago. And these are, actually when Lauren Bennett was explaining this demonstration, she mentioned she was talking to the New York Fire Department. And this is a gigantic problem. Like if they need to prioritize which parcels in New York City they're going to inspect, there's many more parcels that they can feasibly actually inspect in any given year. They're not going to be able to go to every single location in New York City and inspect it and make sure that it passes specifications. So they need to prioritize, and anything better than a random dart being thrown is much better than what they have, right? Even just the fact that they have inspected a location maybe improves the safety. The fact that they may be aware of how the facility is configured, or like the blueprint of the house, or what it's like, or the fact that they're scaring people into passing inspections is much better. So in this case, we're going to use that. We have a data set of essentially previous inspections that have passed or failed. And once again, we're going to open up generalized linear regression. We're going to pass our field for passing or failing, called binary. And then for the model type, this is where now you change it from continuous to something like logistic or binary. And we have a few different explanatory variables in this case. The days since the last inspection, crime density, total crime index, vacant housing units, owner-occupied housing, restaurant density, sales volume, etc. So let's go ahead and run that. And like before, we're always going to be checking our results messages. Let's go ahead and expand that. So our deviance explain is not very good. This is a little bit of a rough model, perhaps not even better than a random dart being thrown. So we can also take a look at a different way to actually run logistic regression, which once again is geographically weighted regression, which has received this upgrade as well. So we're going to pass our input features, and I'm actually going to go back to my tool history to select that. And in this case, it's quite similar. You pass your input features, you determine your dependent variable, you change your model type to binary or logistic, and we're going to select the same features, but now it's going to have that local equation effect for binary. For the number of neighbors, in this case, you do have to once again make that consideration of that neighborhood. And we knew that in a previous round of Golden Search that the number of neighbors that was optimal based on that AIC evaluation, AICC, was 127. So if you've iterated enough, you can simply pass that value that seems to be optimal for a new iteration. So let's go ahead and run that. And all of these tools, as a byproduct, you get a lot of outputs. It's not just the layer that you get on your table of contents. You get the messages window, and you also get a lot of charts by default. So we're going to take a look at all of that. So let's expand our messages window. Let's make it a little bit bigger. And we're going to scroll down. So now there's a few additional model diagnostics. There's a deviance explained by the global model, non-spatial, the one that we ran before, but now there's deviance explained by the local model. So it's improved quite a bit, just the fact that we're now having these local relationships be assessed individually. And if we take a look at the outputs window, you take a look, the default symbology is deviance residual, but you can also take a look at these charts under the layer. So you get a scatter plot matrix that gives you a sense of all of the different relationships between all of the variables. So you can select specific relationships if you want to evaluate further. You also get a distribution of explanatory variables. So let's take a look at that. And I'm going to dock it over here on the side and collapse this. And this is quite interesting. So for variables that have, essentially it takes a look at which ones were categorized as failing or passing. And then it'll give you a sense of the distribution of all the explanatory variables and their ranges for each of the output values. So you can get a sense of, okay, if passing and failing is quite different for the distribution of a specific variable, that could be a really good explanatory variable, right? The one that stands out to me a little bit, if I expand this a little bit, is days since the last inspection. For the ones that passed, they have very few days since the last inspection, but for the ones that failed, they have quite a few more days, right? You can also re-symbolize the output. So in addition to this deviance residual symbology, we're going to go ahead and take a look at symbology. And you actually get a field called probability of being 1. Because it's logistic regression, there's a continuous range of between 0 and 1 in terms of being assigned a value. So let's make this a little bit easier to see. Perhaps we'll use something like this. And once it's done symbolizing, I'm also going to reorder a little bit. So let's go here. What I care about more if I was in the role of the fire chief there would be these locations that have a higher probability of being 1, right? This could be kind of a better way, better than random at least, chance of determining which locations I really need to focus on for a first pass. And that's an example of logistic regression in ArcGIS. Now, for the next case, I'm actually going to go over to the podium, and we're going to do a little switcheroo of microphones. Thank you. Thank you. OK. Wow, that sounds different. So I have the great privilege of introducing a brand new tool that the spatial statistics team has worked really hard to put together. It's called local bivariate relationships. And it works with a concept that this measurement of a relationship really depends on where that relationship has been measured. And this is straight out of the white papers that actually were the basis for this tool. The way the tool works at a high level is that you have two variables. It's bivariate. You have a dependent variable and an explanatory variable. And the tool will do two primary things. First, it will determine if there's a relationship significance, if these two things are actually related, if they have, quote, a good relationship, or something that we can explain or use to explain one or the other. And then it'll categorize the type of relationship that you have. So we'll go into that, but you get as a result a map of relationships across geography. And this can be really useful if you're trying to evaluate a potential model, right? So what does it mean for two variables to be related to each other? We've already looked a little bit at that earlier, but in this case, the tool is going to work with both good relationships, perhaps this linear relationship or the quadratic relationship, and try to differentiate those from null relationships, right? Things where one variable does not necessarily explain the other variable, where you don't really learn much about the other one. And in this case, the tool at its core works with an interesting concept called entropy. So good relationships generally have low entropy. Null relationships have generally higher entropy. And this is very much a metaphor. But the entropy has its roots in thermodynamics. So while it's not exactly like this, it really helps to kind of wrap your brain when you think about it a little something like this. So a single variable has entropy. It's a measurement of how predictable that variable is. And in this case, you can see that things are fairly ordered. You can generally see where every little molecule is going to be a few seconds from now. Now, if we increase entropy, if we increase chaos, if we make everything a little bit less predictable, you have a higher entropy. It's a measurement of how much you can predict something. Now, two variables in comparison, we're going to make things a little bit, we're going to measure the entropy, and things seem kind of fairly unpredictable across those two variables. But if we actually measure the entropy for the two variables together, we may find that there's a little bit of shared chaos. You can actually measure how disordered things are for one variable versus the other just by looking at the other one. So if you add up the individual entropies, and individually, they're going to be higher than if you take the total entropy of the two variables combined. This concept is called information gain or mutual information, the sense that there is shared chaos and therefore you can learn something about the other variable. And that is very useful when you're trying to measure if there is indeed a good relationship, right, for our purposes. And in this case, an analog for measuring entropy is minimum spanning trees. So how do we know if that relationship is actually significant? There is a null hypothesis that we're testing for. But really, behind the scenes, there's a concept called permutation-based distribution estimation, which scared me when I first read that entire title, but we're going to simplify it and break it down a little bit here to really comprehend it. So the tool starts with a feature. That feature has two values in this case, a dependent and an explanatory. And the relationship between y and x is evaluated once again for that neighborhood. So we will take that neighborhood, we will examine the distribution of the variables x and y, create our minimum spanning trees, and measure the entropy. And then the null hypothesis is that, or the question we're going to ask really is, what is the probability that that observed entropy value exists while those two variables are actually independent of each other? So we have that one observed local entropy for that one neighborhood, right? The way we're going to do that is we're going to create a distribution of other entropies where those two values are actually independent. And the way the tool does this is essentially by shuffling the values of the dependent variable y while keeping the explanatory values the same. Then it's going to calculate your minimum spanning trees and get another entropy value. And it's going to do this several times for however many permutations you tell it. By default, it's like 199. But once it does this, you get this nice distribution of entropy values. And your observed one is going to be somewhere in that distribution, right? So if we bring this over, we're going to have our distribution, and we convert it to a p-value. If it's at the tail end on one side or the other, then there's a higher confidence that we can reject that null hypothesis that x and y are actually independent of each other with that entropy value. So in this case, there's really a very low chance that these two are not related. So entropy is just used to determine if these two things are related, right? But it doesn't tell us yet what type of relationship you have, which is very important as well. So the tool kind of has a second act to it. It will classify the local relationships, and it'll summarize all of that information into these categories. It can be positive linear, negative linear, convex, concave, quadratic essentially, or undefined complex, because entropy will also give you an assessment of those types of relationships, or perhaps not significant. So the way it does this is first it starts with the distribution of the significant features neighborhood. And it'll estimate an OLS model for that and calculate the AIC. Then it will square the explanatory variable x, and we will compare these two. Essentially, that second check is checking for a quadratic model. And it'll select the one with the lower AIC. That is used then in this little decision tree, essentially. We start first with this question of, is the r-squared value greater than 0.05? If not, then basically neither linear nor quadratic really fit there. It's just a little bit too complex for us to say anything there. So that's the output. But if it is greater than r-squared for one of those two models, we check, okay, which one was it? Was it linear? Was it quadratic? And then what was the sign of the coefficient? And that lets us end up with one of the linear or convex concave relationships. And the tool really iterates over your entire data set. It'll take a feature, create a neighborhood, check the entropy, check the type if there is significance, and then determine an output for that feature. In this case, it was positive linear. For the next case, it may be convex. For the next case, it may be negative linear, or it may be not significant, until you get your map of local bivariate relationships. So for a demonstration of how this works, I'm going to hand it over to Flora.
All right, thank you. Those slides were really beautiful, weren't they? Okay, so here we're looking at air pollution measurements on the coast of California, around the Long Beach area, around LA. And I want to know if there is a relationship between air pollution and household income. So the air pollution here is measured by PM 2.5, which is particulate matter. And I can see where we have these higher values of particulate matter in kind of like the valleys. And then I can turn on my household income layer, and I can see where we have higher income. And by just kind of visually comparing these two, I can't really tell if they're related. And in this case, really, those relationships are going to vary from place to place. I can't really model the relationship between these two as one global measure. So I'm going to use the local bivariate relationships tool. I'm going to input my features. My dependent variable is going to be air pollution, and my explanatory variable will be household income. And then I'm going to go ahead and run the tool. So the tool is going to go and pick each feature, look at its neighbors, see if it can find a relationship that's significant, and then it's going to determine, okay, there is a relationship, what type of relationship is it? And then it's going to symbolize my map describing those 4 different types, well actually 5 different types of relationships that it could be. So we see here that in these darker pink areas, we have a positive linear relationship. And, I'm going to run this tool one more time. I accidentally saved it as a shape file, which I did not mean to do. So I'm going to save it as a feature class, because with the feature class, we get some really useful pop-ups that help us interpret the results. So, but looking at this result here, we see that all of these gray areas, there was no significant relationship. So income and air pollution, obviously one is not causing the other, but perhaps people with higher income have the privilege of choosing to live in a place with less air pollution. But we do see that where we do have relationships kind of ends up being in these foothills, right along the edges of the valleys and kind of getting up into the foothills. So along with getting a better view, when people move up there, they're also getting cleaner air. All right, so my tool has run again, and now I can explore those local relationships. So the areas in this darker pink, these are positive linear relationships. So as household income goes up, in these areas, air pollution values also go up. In the dark green areas along these foothills, we see that negative linear relationship. So the more household income we have, the less air pollution we have. And then we have some areas that have a little bit more complex relationships. Like, I think it's pretty interesting in these light pink areas, we have concave relationships. So we see that U shape. The relationship actually flips. So with the lower values of household income, there's that positive relationship. And then when you get to higher values of household income, it goes down. So these visualizations really help us decipher the meaning of these different relationships. And then let's take a look at, we have some convex relationships also. So that's kind of the opposite U shape. And even though we don't have a spatial relationship everywhere, we can see kind of clustering of relationship types along these physical features in our map. And that's because air pollution really is affected by the physical terrain, right? Particulate matter can kind of get trapped in between the mountains and the valleys. And then also, household income can be affected by, household income is not affected by where you live, but household income allows you the privilege of choosing where you live. So a lot of these nice places in the hills are gonna have higher income and then less air pollution in these negative linear relationships. And then we have a couple places that are symbolized in these yellow, which are undefined complex. So there is some sort of relationship there, but like the entropies together have information gain, but it's not quite as simple as drawing a quadratic or linear shape. But there is some sort of relationship there. So we can explore those by looking at these pop-ups as well. And what I think is really neat about these pop-ups is that you have all of the different features that belong to the neighborhood, and then the one feature that you clicked on is highlighted. So you can actually really get a good understanding of this idea of a neighborhood and what's proximate, and explore how these different relationships work. So that's a neat one. New addition to the spatial stats toolbox. All right, I'm gonna flip it back over. And we always like to end this session with one of our favorite quotes, which is that essentially all models are wrong, but some are useful when properly specified. Okay, so we are on Day 3. So lots of our sessions have already happened, but we have a couple more. At 1 o'clock, you can learn about machine learning and ArcGIS. At 2:30, we have a talk on data visualization for spatial analysis. And then at 4 p.m., we round out the tech workshops with Forest for the Trees, which is about the random forest algorithm and how we can use that to make predictions. So here we talked about those linear regression methods. There we're going to talk about that machine learning method, and it's a pretty neat one. So if you would like to come by and check that out, we'll be here. Also, if you didn't get to catch all of our sessions and you're still curious about something that we taught, you can go to esriurl.com/spatialstats. And all of our sessions that we've taught have already been recorded from previous years and are up there. We have a little bit of new material this year, but most of what we've taught is already online. And then as soon as we get the recordings for these sessions, we'll put those online too. All of the slides that you saw, those are going to be online. So you can go back and learn more about this. Also, links to the help documentation is up there. So if you want to learn more, and then please fill out a course survey if you wouldn't mind. You have to do it through the app now, but we use your feedback to justify what sessions we teach in the future. We use your feedback to improve our sessions. We also use your feedback to justify which sessions should be recorded and put up on YouTube for free. So you may have noticed that there are some papers on these chairs that you can buy, the recordings of these sessions. We really lobby each year to have our sessions put up on YouTube for free because we think it's really important. And because we get lots of great feedback from our users, we can justify that our sessions deserve to be online for free. So your feedback helps us with that as well, and we really appreciate it. We really enjoy reading your notes. And lastly, I'll mention that we have people at the Spatial Analysis Island every minute that the expo is open. So if you didn't have a chance to ask your questions during the workshop, sometimes we'll come up between sessions and we're kind of rushing to get to our next session and we can't really go in depth into your really interesting questions. Just go down to the island and someone who either wrote the code for the tool or who designed the tool or who wrote the documentation, there are people that are experts that are there right now who would love to sit down with you and go through your workflows and really spend some time with you and go into detail to answer your questions. So check that out if you'd like. And thank you for joining us. We'll see you at the next session.